thank the organizers.
Let me mention that Marco is the winner of this year Lichnerowicz Prize. So my pleasure is doubled by the fact that Lichnerowicz's family came to France from Poland. So.
Thank you, and thanks especially regarding the Lichnerowicz Prize. I have a particular fondness for Lichnerowicz, not only for his work in Poisson Geometry, but also for his work in Riemannian spinors, which is some of the first papers that I read when I was a student under Hitchin, whose thesis was all about Lichnerowicz's work. I wanted to thank Enrique for having a perfectly organized conference so far. We're still watching. And I also just wanted to thank the other organizers, people on the committee who remain in the shadows, and I just wanted to single out Alan Weinstein for kind of introducing me to this community. I spoke to him, one day about generalized complex structures, and the next thing I knew, I was coming to Poisson in 2004. I don't think it's a coincidence that happened. So thank you for that. Okay, so today I'm going to be speaking about generalized scalar geometry, which seems every time we kind of dig deeper into it to reveal more structures. And certainly we're not at the end of the story. There's many unanswered questions about this geometry. It's been around basically since 1984 in one form or another, but there are still strange behaviors that we don't fully understand. I put a paper on the archive just recently, and everything that I'll speak about today will be contained in there. So let me know if you find any errors, of which I'm sure there are some. Okay, so the first thing I want to start with is, so actually I've selected some excerpts from this paper, which I hope will be useful more generally. So maybe you don't care about generalized scalar geometry, but you may care about some of the tools that I had to develop in order to study it. Okay, so the first thing is holomorphic courant algebroids. Okay, so I'm going to define, okay, are you ready? I'm going to define a courant algebroid, an exact courant algebroid. Okay, an exact courant algebroid, so you're expecting the 5 axioms, but I'm not going to write them down, is an extension like this, right? With a symmetric pairing, which I'll just write like this, the way we normally do. And I'll write it in this way. So the symmetric pairing should give me an isomorphism from this sequence to the dual sequence, where this is just the identity map Okay, so this is also just the identity map, like that. So I want this to be an isomorphism of extensions. So not only is this a inner product, but it preserves the extension structure and a bracket. Okay, which is usually called the Courant bracket, and on its sheaf of sections. On its sheaf of sections. Okay. And locally isomorphic to the usual Tn. Okay. I think that's all you really need to say. You just want to say that you have to be familiar with the structure. Right, when I write this double bold T, I just mean Tm plus T star m. The point is that the usual Courant bracket, which was written about by Alan and Ted Courant, was on T plus T star, and T plus T star has natural structures, including a symmetric pairing and a bracket. And a Courant algebroid is just something which is locally isomorphic to that. So you don't really need to be writing down all the axioms. They follow from this. Okay. So the reason why it's nice to write it this way is because all you need to know in order to classify these things is, these are things which are locally isomorphic to some standard model. So in order to classify them, all you need to know is what the automorphisms of the standard model are. So since the automorphisms, the sheaf of automorphisms for the standard model is the sheaf of closed two forms, which I'll denote this way. Okay. This means that Courant algebroids, so these are classified. So whenever you have something which is locally trivial and whose local automorphism sheaf is something, a sheaf of some groups, in this case is a sheaf of abelian groups, then the objects are classified by H1 with values in that sheaf. So this is not a D, it's a CL for closed two forms. So in the C infinity category, okay, then this sheaf has a nice acyclic resolution. So this is the two forms which are closed. But these are exactly the kernel of the D operator going from omega 2 to omega 3. Okay? So this means that H1 of this is the same as H1 of this complex, which is exactly the middle term here, so it's exactly the third cohomology. So this means that we get H1 of omega 2 CL is exactly H3 of M with either real or complex coefficients, depending on whether this thing is going to the complexified tangent bundle or the real tangent bundle. So this is the Chavera classification. So this is the... Okay. So in the holomorphic category, I'm just going to repeat the same thing. I'll just repeat the Chavera classification. In the holomorphic category, the problem is that in the holomorphic category, things are more complicated. This is no longer an acyclic resolution, so we can't just deduce this. And this sequence may not split at all. There may not be any splitting of E into T plus T star, even though in the smooth category there is such a splitting, right? So in the holomorphic category, you need to be a little more careful, and you have to say, well, the closed two forms, these are, so this sheaf is different, right? This is the holomorphic closed two forms. This is just the closed two forms. In the holomorphic category, we need to use holomorphic closed two forms. Or maybe I'll put a little HOL there to indicate that. So what are these? So first you need to resolve the fact that these are holomorphic. So you need to use the fact that they're not just two zero forms, but they're actually in the kernel of the Dolbeau operator. Right? 2, 1, 2, 2. Okay. But then you need to resolve these sheaves. So we use the normal Dolbeau resolution for that. So this goes to 3, 0 and to 4, 0. Right? And this goes to 3, 1, like that. So this sheaf has a resolution which is more complicated. It's a double complex. And so if I want to take H1 of this, so this means that H1 of this of 2 closed is equal to H1 of this complex. Okay, so this means that you're supposed to take something from there. So something from there, I'll call it H, and something from here, I'll call it T. So this means that what you need for a Courant algebroid is this H plus T, such that it's killed by D. Okay, so this determines the holomorphic Courant structure. Okay, so let me give you an example. Let me give you the universal example of this. So example 1 is going to be, let's say we take X is a complex manifold, right? And we take now T10 plus T star 10. Okay, so these are the holomorphic tangent bundle and the holomorphic cotangent bundle. And both of these are holomorphic vector bundles over a complex manifold. But we can change the holomorphic structure on this bundle by giving a deformation of the d bar operator. So we're not going to consider this to be, but not the usual holomorphic structure. It's the one given by this operator, which I'll call d bar. So this is the usual Dolbeau operator, which just tells you the normal holomorphic vectors and covectors. But here, what I could do is put this tensor T in there, and you can check that this is a different Dolbeau operator. And then the bracket of x plus c, these are now 1, 0 vector and a 1, 0 form, which are holomorphic with respect to this operator. This will be the usual x plus c, y plus eta, the usual Courant bracket, plus this term ix, iy, h. So h is the 3, 0 tensor here. So using h and t, we produce a holomorphic Courant algebroid by deforming the complex structure on this bundle and defining the Courant and defining the Courant bracket in this way. Okay, so that's what a holomorphic Courant algebroid looks like. So any questions about that? I'm going to give another example. Let's see. I'll give it here. I just can't take those any more papers which have the 5 axioms written down. You just shouldn't just keep writing them. I mean, I've done it myself, so I'm guilty, but. Okay, so example 2. Okay, so imagine that we take the Hopf surface. This is a really nice example. So the Hopf surface is obtained by taking C2, removing the origin, and then quotienting by saying that Z1, Z2 is equivalent to 2 times Z1, 2 times Z2. Okay, and what it looks like is like that. The spheres in C2. So this is C2, and I'm making an identification of the unit sphere with the 2 times the unit sphere. Okay, so as a topological space, X is isomorphic to S3 cross S1. The S3 is the unit ball in the unit sphere inside C2, and then you have the S1 because the radial direction is periodic boundary conditions. Okay, so on here, if we look at this complex, so that has a natural complex structure. It's a surface. This is a complex surface. Well, it's a holomorphic complex surface. And if we look at this, then this whole top part here is just a bunch of 0 vector spaces. This is all 0, and all you have is this bottom line because of the dimension. It's a surface, so there's no 3, 0 or 4, 0. So all you have is this, and H1 is exactly this group. So what is the Hodge diamond of this thing? It's exactly, it's exactly like this, where this is H01. Sorry, did I get it right? So this is H01, and this one is H12. H21, sorry. Okay, so there's only 2 Betti numbers which are non-zero, and luckily it's exactly the one we need. So H21 is giving us one class exactly here. So that means that there's a 1 parameter family of holomorphic Courant algebroids on this thing. So this tells us that there's a one-dimensional family of holomorphic Courant algebroids on here. So what are they? An easy way of seeing what they are is like this. So take, let's divide this into two open sets. U0 will be the whole Hopf surface minus Z1 is equal to 0. Let me call it U1 and U2. And this will be X minus Z2 is equal to 0. So the two open sets, one of them does not have Z2 equals 0, and the other one is missing this locus like that. So there's two loci given by Z1 equals 0 and Z2 equals 0, which I can remove and get open sets inside. And I'll use those two open sets. And I'm going to give a two form, B12, which is defined on the Hopf surface. Okay, so notice that this is a two form, which is smooth everywhere except the red and purple loci. And it's invariant under multiplication by 2. If I multiply Z1, Z2 by 2, this thing stays the same. So it descends from C2 minus 0 down to the Hopf surface. Okay? So this thing is a holomorphic 2-0 form. And I can use it to build. This is another standard way of building a holomorphic Courant algebroid. So I could take T plus T star of U1 and T plus T star of U2. And then on the overlap, you just glue them. You glue using B12. And this produces you a holomorphic Courant algebroid. And all you need to do is, in order to get the parameter family, you can just multiply by a complex number. Okay? So this is another typical way to produce holomorphic Courant algebroids. Okay. The second, okay, so that's part one, holomorphic Courant algebroids. So the second part is actually a different way of producing holomorphic Courant algebroids, which uses a technique which is called Courant reduction. So we, in a paper with Enrique and Zhu, we developed a technique whereby you can do symplectic reduction for Courant algebroids. And so how can we do, part two is holomorphic reduction. Okay. So let me make a definition. Suppose that you have a Courant algebroid, an exact Courant, all my Courant algebroids will be exact. So it's a Courant algebroid over a complex manifold X. Okay? But I'm not going to assume that it's a holomorphic Courant algebroid. So let me say it's not non-holomorphic Courant algebroid. And I want to describe how to put a different way of putting a holomorphic structure on it in a natural way. Okay, so how can we put a holomorphic structure? So the definition is, if we have one of these Courant algebroids over a manifold, then a lifting of Tx01 is a subbundle of E, okay, such that the projection, the anchor map of E, if I restrict it to D, gives me an isomorphism to T01x, and D is involutive and isotropic. Okay, so D is the reason I called it D is because it's almost like a Dirac structure. It's an isotropic, involutive subbundle of the Courant algebroid. It's just the wrong dimension. If you look, this is an isomorphism to T01x, so it's half the dimension of what it's supposed to be. So it's just a little mini Dirac structure. Okay. Okay, so if you have a lifting, the reason that I made the definition is because the lifting defines a kind of like an action of T01x on the Courant algebroid E. Okay? You can imagine taking a section of D and acting by the adjoint action, just bracketing against a section with E. Right? So the sections of D act on E in the language that we had in our paper. So there's this action. And the idea is that we would like to reduce under this action. We want to quotient by the action. So you should think of it like these are like anti-holomorphic directions, and we want to get rid of them. We want to remove the anti-holomorphic stuff and be left only with holomorphic stuff. So the reduction is defined like this. It's called ED. Just reduce that D. This is going to be D perpendicular divided by D. As a bundle, it's just D perpendicular divided by D. Okay, so you can see here that because I'm taking something isotropic and taking D perp mod D, this will inherit a pairing from E. So this will be a bundle with an inner product. Okay, but D perp, if you look at where D perp gets sent, it's actually it's surjective onto TX cross C, and D by definition gets sent to T01x cross C. Okay? So this means that the quotient will be sent to the quotient, which is exactly the holomorphic tangent bundle. So this means that D perp mod D has an anchor map, it's an anchor map, down to T10x. And in this way, we get this extension that we wanted, like this. Okay? Now, so fine, we have an extension and we have a metric on it, but what about the bracket, and more importantly, what about the holomorphic structure? Well, the holomorphic structure is gotten by the, it's kind of like what Yvette said yesterday, just use the Courant bracket for everything. So the Courant bracket gives you the holomorphic structure if x01 is a section of T01x, then, and E is a section of this ED, then we define D bar. So in order to differentiate E, the section E, okay, we define it to be just the bracket of x01 with a lift of E modulo D. Now, when I say this is the Courant bracket in the Courant algebroid, but this has to be mapped into D. So I'm going to say that you take the projection map, restrict it to D, and take the inverse, so that this vector field downstairs gets mapped into D by the isomorphism, by the lifting. So this is the lifted anti-holomorphic vector field, and then we take the bracket against some lift of E E is a section here, so the lift of E is a section of D perp. So this is a well-defined, this is similar to the bot connection. It's a way of using a bracket to deduce a partial flat connection. Okay, and then the Courant bracket just descends to the holomorphic sections. You can see that. Okay, so just by finding a lifting of T01, it immediately puts the structure of, it allows you to reduce and produce a holomorphic Courant algebroid. Okay. All right. So any questions about that?
So what is E real Courant algebroid field? So that E there.
E could be real, and then in order to have a lifting, right? If E was real, then you would just complexify it. If it's complex, then good. That's fine.
Just there. You wrote T01
Oh, sorry, yeah. Thank you. Yeah, it's just this in here. This is a surjection too. Thank you. Okay, so, all right, so that's all I wanted to say about that. Okay, so now let's go to generalized scalar geometry. So, okay. Uh-huh. Yeah, good question. So, yeah, so there's a simple cohomological obstruction. If you look at the sequence like this, you should look at a sequence that looks like this. The holomorphic functions. There's the D operator going to 1 forms. This goes to closed 2 forms to 0. So if you think of the columns, this is an exact sequence of complexes of sheaves. Okay, and what this tells you is that H3XC maps to hypercohomology hypercohomology 3 of this complex. This is not really that important. That's why I didn't really want to. And then and then if you look at the sequence, we just get H1 of omega 2 closed. Okay, so just as an aside, okay, if you have a Courant algebroid, and if this class vanishes, then it comes from a holomorphic Courant algebroid. So these are the holomorphic Courant algebras, and so whether a lifting exists is whether this class vanishes. Okay, so it's just a kind of simple cohomology obstruction. Okay, so now let's get to generalized scalar geometry, where we're going to hopefully use all of this stuff. Okay, so if we have an exact Courant algebroid, let me call this M the manifold, an exact Courant algebroid, okay, then what is a generalized scalar structure? We have to have 2 generalized complex structures, are generalized complex structures. So these are complex structures on the Courant algebroid. They square to -1, and their plus I eigenbundles are involutive. But they need to commute. They must commute. One point is that they must commute. And the second point is that they must be positive in the sense that if you combine them with the pairing, that must be positive. Okay? So we just have a pair of generalized complex structures which commute and which satisfy some non-degeneracy condition. Okay. So without giving any more details, I'm going to see how we're going to get this data that will lead to a splitting, a lifting, and therefore to a holomorphic Courant algebroid. Okay, so the point about this commuting is that the eigenspaces of J1, so this is a classical thing, eigenspaces of one operator will decompose as eigenspaces of the other. Under J2. Okay. That's the reason that we want the commutation. So J1, it gives me a decomposition like this. E tensor C breaks up as L1 plus L1 bar, where this is the plus I, eigenbundle. Okay. And J2 gives me a similar thing with L2 plus L2 bar. Okay. And then, so since these 2 decompositions are compatible in the sense that they're given by commuting operators, then what happens is that you get a decomposition into 4 spaces. So you get L plus L minus plus L plus bar plus L minus bar. Okay. And this piece here, this is L1. And this piece over here, L plus together with L minus bar, this gives me L2. Okay, so as you can see, L1 and L2, they share a bit of the plus I eigenbundle. So this L plus is the common plus I eigenbundle of both J1 and J2. This one is plus I for J1, but minus I for J2. So, but you can see that the eigenspaces kind of coincide, but with different eigenvalues. Okay, so, all right. So this decomposition gives a lot of structure. Okay? So if you think about it, these are Dirac structures. All of these four things are Dirac structures, complex Dirac structures. And these are the intersections of Dirac structures. So they are not Dirac structures, they're too small, but they are integrable. Okay? They're integrable, and not only that, but you have two of them which sum together to give you a Dirac structure. So there's many people here who are familiar with this situation. It's called a matched pair of Lie algebroids. This is a Lie algebroid since it's the intersection of two Dirac structures, both of which are Lie algebroids. So these are, all four are Lie algebroids, but the sum of these two gives me another Lie algebroid. So that's a matched pair. So I'm not a big expert on matched pairs, but I know one when I see one. It's a matched pair. So there's a whole bunch of matched pairs here. And I'm going to, essentially what I'm going to do next is I'm going to analyze the matched pair, but in an unusual way. I'm going to analyze it by reducing along one of the members of the matched pair. Usually you don't do that. You just kind of use both things in the matched pair together. But I'm going to get rid of one element of the matched pair and see what happens to the other. Okay. So, so if you look at L plus minus bar, or just let me just take one of them, L plus bar. Okay, this is, like I said, it's too small to be a Dirac structure, but you can show that if you project this under the anchor, what you get is the plus I eigenspace of a complex structure. So this gives me T01 M for a complex structure, a usual complex structure. I plus, and if I use L minus, then I'll get another complex structure, I minus. So this is the some people will be familiar with this, that you can get a bi-Hermitian structure out of this. So the idea is that these things inside the current algebroid, maybe it's not obvious what they mean, but if you push them down to the tangent bundle, they give you integrable subbundles of the tangent bundle, and if you intersect with its complex conjugate, they don't intersect. So it defines you a complex structure downstairs. So both of these define complex structures downstairs. Okay, but the nice thing is that, so I'll call these complex manifolds. So this means we get complex manifolds x plus minus. Okay, so kind of you should think of it like this, that M is diffeomorphic to some other, I mean, these are all diffeomorphic, but these are complex manifolds. So this is in the holomorphic category, and this is in the C infinity category. Okay. And I really want to emphasize that now that we have started, through various works of many people, including Hitchin and Goto, we have many examples of generalized Kähler structures. And in some of those examples, these two complex manifolds are not isomorphic as complex varieties. So you can have a smooth manifold with two completely non-isomorphic complex structures on it, like, for example, P1 cross P1 on S2 cross S2, or the second Hertzebruch surface. They're different complex manifolds, but they exist on the same smooth manifold, and this can occur in this setup. So the meaning of that is not fully understood today, I don't think. The reason why you get these two, in a sense, what can you do with these two complex structures? We don't know yet. Okay, but the nice thing about these complex structures is that they come with a lifting. They came, in fact, from a lifting. So the T01 actually is inside, embedded. So they're natural liftings for T01 plus minus given by L bar plus minus. So these really are, you could think of them as being liftings. So that means that we should think of these as an opportunity to do reduction. Let's reduce along with both of these. So just applying the second, part 2, we can reduce. So this tells us, reduce. And what this tells us now is that this original courant algebroid, it reduces to a holomorphic courant algebroid on X plus. And if you chose the L minus bar, this would give you another. So this is reduction along L bar plus, and this is reduction along L bar minus, going to E minus over X minus. So you obtain two holomorphic courant algebroids by doing these two different reductions. Okay? And they both kind of came from the same underlying smooth courant algebroid. Okay, but and the isomorphism class of this courant algebroid, of these two courant algebroids, okay, it's obvious that they should be, you should be able to easily deduce what the isomorphism class is of this from the Chavera class of this. So it's indeed true that these are given by the Chavera class of E taking the 2-1 part with respect to the two complex structures I plus or I minus. Okay. So I'm not sure how to phrase the theorem which includes all this information, but just it ends there. Okay. So any questions about the origin of these two holomorphic courant algebroids? Yeah. So if I reduce under this, I'm supposed to take its perp mod itself. So the perp will include L plus bar and L minus. The only thing that is not in the perp is the thing which is complex conjugate to it. So this is not there. And if I mod this out, then these two, let's see, this is L1. So this means that this thing will give me epsilon minus, and the other one will give me epsilon plus. Is that more or less clear? You're already foreseeing the next step. I mean, it's suspicious when you have a courant algebra decomposed into two pieces. Okay. So the next step is that, so not only do we get these epsilon plus minus, okay, but I mean, this is a reduction. So in the philosophy of doing symplectic reduction, if you have some structure, like let's say a Lagrangian upstairs, you can reduce it. And anything you have upstairs, you try to reduce it. So here, we're reducing along something, that's fine. But we had these many Dirac structures. Therefore, we could take one of these Dirac structures and pass it down to the quotient, to the reduction. So not only do we get these, but we can reduce the Dirac structures, the honest Dirac structures. Okay, so L1 and L2. Okay, and okay, so what do you get when you do that? So let me just decorate here. So this is, we have the E minus on here, and we have the E plus on there. Okay. So if we reduce these, so reducing, okay, what are you supposed to do? You're supposed to take the Dirac structure. You're supposed to intersect with L minus bar or L plus bar, perp, and divide by L1, intersect L plus, and this goes into E plus. Right? That's if you're familiar with the way you do the reduction, since this is defined by L plus perp mod L bar, then in order to get a reduction of a Dirac structure, you just do the appropriate intersections, and that defines you a Dirac structure downstairs. So this gives me something I'll call, let me see, I'll call this A plus. And then we also have B plus, which is obtained from L2. So L2. So I'm just doing I'm just looking at E plus now. So this is inside E plus also. And indeed, if you follow it out, then what I get inside the E plus is a decomposition which corresponds to this decomposition here. The point is that there are two Dirac structures and they pass down to E plus. So this tells me that E plus is a sum of two Dirac structures which are actually transverse. So these are transverse holomorphic Dirac structures. So we had no idea that generalized Kähler geometry had this inside it. Not only does it have a holomorphic courant algebroid, but the thing is actually decomposed into a sum of holomorphic Dirac structures. And so from this paper of Liu, Weinstein, and Xu, which is very influential in my thinking, obviously. I mean, I'm always looking for transverse Dirac structures because of their paper, because they really studied them and showed how many interesting questions there are regarding these transverse Dirac structures. And so what do you get whenever you have transverse Dirac structures? Someone who's not Enrique must answer. What do you get when you have two transverse Dirac structures? What? Oh yeah, Manin triple. What else do you get in terms of the name of this conference, let's say? Okay, too many complicated answers. So you get a Poisson structure. And it's holomorphic. Right, so this was observed by many people, but it appeared first in this paper by Xu and Mackenzie. So they noticed that if you have transverse Dirac structures, you get a holomorphic Poisson structure coming out of there. And this is indeed the one discovered by Hitchin. So this is the Hitchin structure. So it actually is explaining the existence of the Hitchin-Poisson structure on these. So he came to Poisson and he discussed these last time. So yeah, so it really comes out of these two, and it's so this is kind of interesting. I mean, there's the consequences of this. There's many questions that we had about generalized complex geometry, which this answers. Okay, so okay, so the leaves. So, well, okay, these are Dirac structures, and so they induce holomorphic foliations. Since they're transverse, you actually get transverse holomorphic foliations, right? Which means that the leaves of A plus and the leaves of B plus, they always intersect transversally, and they give you leaves of the Poisson structure. So the leaves of A plus and B plus are, holomorphic, transverse, singular foliations, okay, which intersect in the symplectic leaves of the Hitchin structure, of Hitchin-Poisson structure. Hitchin-Poisson structure is called sigma. Okay, so but not only that, these leaves they actually correspond to the leaves, the symplectic leaves of the two generalized complex structures. So I mean, we know that they're holomorphic Dirac, but also the leaves of A plus and B plus, they coincide with the leaves of J plus minus, J1 and J2, the two original generalized complex structures. So a priori, we had no reason to believe that if you look at the real Poisson structures underlying these two things, if you look at their symplectic leaves, these are real symplectic leaves. There's no reason a priori to imagine that they're holomorphic. But they are holomorphic, and everything about them is holomorphic. Their intersections are holomorphic symplectic because of this Poisson structure. So it tells us, it controls the behavior of the two generalized complex structures in a very strict way, something which we don't have for generalized complex structures. Okay. Okay, so so notice that here I've said everything for E plus. The same thing is true for E minus. So both of these become decomposed into some of Lie algebroids. And the relationship between the Lie algebroids here, this is A minus plus B minus. This is A plus B plus. Okay, and the relationship between A plus and A minus is like a Morita equivalence. I explained this in the paper. And the relationship between B plus and B minus is a conjugate Morita equivalence. You just need to take complex conjugation, which is an issue that comes up a lot in holomorphic courant algebroids. Okay. Yeah. Well, these are holomorphic Poisson structures. They're on completely different complex manifolds. Sigma plus and sigma minus are on totally different. Now, if you take their imaginary part, they coincide. Yeah, that's right. They coincide, and that was observed by Hitchin. That you have two holomorphic Poisson structures which coincide in their real part. Okay. All right. So. Okay, so I could say more, but I'm just going to cross it off, and let's go to gerbs. Because there's something useful in the gerbs section, which I think some people might disagree with what I'm going to say, so hopefully you can be gentle in your criticism. Okay, so part 4. So if you're sleeping, you can wake up for. This is totally unreal. Well, it's unrelated, more or less. So this is gerbs.
Could I ask a quick related question?
Yes.
Did you say that the Algebra class projected the 3 zero-component matches?
I didn't say that, but it's true.
Oh, you wrote it?
I didn't write it, but it's true. It's so true that you probably saw it in your mind. Ah, I see what you mean. Okay, yeah. Okay. So just very quickly, I'll say that if you take the 3 form, so the point is that when you have this generalized Kähler's geometry, you get I plus and I minus, and you get a Riemannian metric, which basically is coming from, okay, and I haven't used the metric yet. So the metric comes from that fact that there was a positivity condition, and you get a metric on T. So out of the metric and I plus, you get a 2 form, omega plus, and dc of omega plus is the 3 form H. So this implies that it has type 2, 1 plus 1, 2, just because it's dc of omega plus. Omega is of type 1, 1, so this only increases by 1. Okay? Yeah.
Now that that question was asked, then there's something related to that question.
Yeah.
So these current algorithms that the holomorphic ones that you're describing now,
Yeah.
T plus T star on this Hermitian setup, twisted by this H, either plus or minus.
Twisted by H, but also by, well, actually, so there were 2 things that needed to be twisted. There's a T plus H. T twists the holomorphic structure, and H is a 3-0 form.
I'm thinking now on these very precise ones that you get out generalized scalars.
Yeah. So those are extensions of holomorphic T by holomorphic T star, but they're not trivial extensions. The extension class coincides with this 2-1 form. This thing here has a 2-0. If you take the 2-1 part, that's the extension class.
So, because we use this with that thing, we use exactly the same extension. So now the question is this the same or not? That if you take the resolution of your bicomplex, what you call in this paper on the
maybe we should talk about it later. I'm not going to be able to finish the. Is it okay? Okay. All right, so I just wanted to say this thing about gerbs. So a C-star gerb is a sheaf of categories. And now you're going back to sleep. I'm sorry. A sheaf of categories which is locally equivalent to the category of line bundles. So this means that over every open set, you have line bundles on the open set. And that's what the sheaf of categories looks like. Just globally, it's not the category of line bundles. It's only locally the category of line bundles. Okay, C star gerb with zero connection is the same thing, category of line bundles with connection. Okay. So just imagine that you have this. So to specify such a gerb, what we'll do is just say, well, locally it's trivial. Locally it's the category of line bundles. But on double overlaps, I need an equivalence from this category to glue it to the other one. And equivalence is given by an automorphism, an auto-equivalence of the category of line bundles, which is just tensoring by a line bundle. So give line bundles Lij on Uij and connections on the Lij, and such that they're coherent. On triple overlaps and on quadruple overlaps, you have the coherence conditions. Okay? So Cevera and Hitchin, okay, they observed that out of this data, you can construct a Courant algebroid. Courant algebroid, which is obtained by taking T plus T star of each open set, Ui and Uj, and gluing them together by the curvature of nabla Ij. And because of the coherence, these gluing maps glue together the Courant algebroid. Okay? Okay, good. I have enough time to explain this fact. All right, so out of a gerb with zero connection, which I can describe in terms of these connections on double overlaps, I can produce this Courant algebroid, E nabla, which goes like this. Okay. And now what I want to study is, so now that I have a one connection on the gerb with zero connection is a splitting of E nabla, which gives rise. So whenever you have a Courant algebroid and you split it, you can check if that splitting is bracket preserving, and then out pops a three form. This is the usual Cevera construction. So which has associated three form H, which is called the curving of the gerb connection. Okay. So the point is that, I mean, the way that I like to think about Courant algebroids is that they help you to understand what is a connection on a gerb. If you give a gerb with zero connection, you get a Courant algebroid. So the Courant algebroid is somehow capturing the structure of the zero connection. Okay? So if that's true, if you believe this story, then you should ask, what happens if I have a Dirac structure in that Courant algebroid? What does that mean for the gerb? So what is a Dirac structure with respect to the gerb? If it's true that the Courant algebroid captures the connective structure. Okay, so what is a Dirac structure? So the Dirac structure is a bunch of little Dirac structures inside these TUIs, which are being glued together by these FIJs to the other pieces of the Dirac structure inside TUJ. I'm just expressing the Dirac structure locally as little Dirac structures being glued together. Okay, and out of this data, I claim, so you can produce an interesting object. So define del ij to be, okay, so take your initial connection, nabla ij. That's a connection where you can differentiate in the tangent direction. If I compose this with the dual of the anchor map of D, okay, this gives me a D connection. Okay? So it gives me a D connection. But so not only do we have a D connection over the Lie algebroid D, but also if I take this, so in the original papers of Weinstein and Weinstein and Courant, they considered the negative inner product, which was x, so C of y minus eta of x. This was the negative inner product on T plus T star. And what Courant actually showed is that if you take this negative inner product and restrict it to di, what you get is a two-form bi such that, and he showed this, it's a kind of a long calculation, which I don't know a very simple way of showing, but such that it's closed. So he actually showed this. So out of the data of a Dirac structure, you can produce a D connection on each Lij, and you can construct Bi such that if you take Bi plus the curvature of del Ij, you get Bj. Okay? So this means that the gerb inherits a flat D connection. Okay, flat because the curving is 0, this thing which is supposed to be the 3 form. Okay, so I never found a use for this theorem of Courant until now, where it shows me that finding a Dirac structure tells me that the gerb is flat in that direction. Okay, all right. So just to finish, the reason why I wanted to talk about these gerbs is because Maxim Zabzin and Rocek and their co-authors, they have a whole bunch of papers trying to pre-quantize generalized Kähler geometry. So, in the same way that you do geometric quantization, they want to understand what does it mean to pre-quantize and quantize generalized Kähler. And of course, the first thing you should do is to quantize the gerb. And that means that you view the Courant algebroid as coming from a gerb in exactly this way, in this gluing way. Okay, but then what I'm trying to say is that the existence of these Dirac structures inside there, it tells you right away, canonically, that the gerb is flat in certain ways. So, for example, it tells me that the gerb is generalized holomorphic for J1 and J2 because of the fact that these have Lie algebroids in that Courant algebroid. But it also tells me that it's holomorphic with respect to I plus and I minus because of the existence of the little l plus bars and little l minus bars. It gives me a holomorphic structure on the gerb. And also it tells me that the holomorphic gerb, G plus minus, are flat along A plus and B plus. Okay. So it tells me that the gerb on the complex manifold is actually flat along these two transverse directions, and therefore it's actually a Poisson gerb for the Hitchin-Poisson structure. Okay, so what it means for this gerb to be a Poisson gerb, I'm not quite sure. I mean, I have a definition which says that it's a flat module. It's a module over the Lie algebroid of the Poisson structure. But I mean, as for the utility of this, I'm not quite sure. But it somehow has to come into this question of quantization. So I'll leave it there, and thank you for your attention.